Okay, so now we have our framework for supervised learning. Let's see if we can apply it to the example that we have of the points on the 1D line. So we've already got the data. In this case, we made it up, but usually you would gather the data along with its labels. The second step is to choose a space of functions. Okay, so possible functions that I could apply to the input here, which is some number on the number line, and then give an output, which is the label. And so in this case, I'm going to restrict myself to a space of pretty simple functions, these piecewise functions here, where I choose a particular number c, and given that number c, I get a function, which is, it gives me a 1 if x is greater than c, or it gives me a 0 if x is less than or equal to c. So I could define this pretty simply as the following method. So I'll pass in the c and I'll pass in the x, and I'll return. So I'll say, okay, if x is greater than c, it gives me a 1. I'll make sure that I actually return this as a float and not just a Boolean. And so maybe I'll say, okay, so the points that I want to look at here are, so I'll say I'll evaluate it between, let's say maybe -4 and 4. Maybe I'll evaluate 200 points there. And let's try c is equal to 1 as an example to begin with. And so let me go ahead, I'll plot this data, but I'll also plot this function superimposed on top of it. So if I were to sample this function, I would say y is equal to that function, c is equal to the c that I chose, and then I'm going to evaluate this function at all the inputs like this. And so let me then plot the function. Let's see what that looks like. Okay, so here's the function for c equals 1, and that actually seems like a pretty good choice. It's saying, okay, everything to the left of 1 is 0, and everything to the right of 1 is a 1. And of course, I could change c. Let me throw it in the plot here just so we can see it. So what if I made c -1 instead? Okay, this seems like maybe a worse choice. It seems like it's labeling more points incorrectly. Right? It's labeling a ton of these blue points as a 1, but they really should be a 0. And so then the question is, well, how do I actually quantify that? And then, of course, that's the third step, which is devising the loss function. We need a way to measure how well that this choice actually fits the data. And so here's the loss function I'm going to define. I'm just going to say, okay, look, on every example that you have, so every example in the data that you have, and actually since the last video I changed this, it's more common to call the labels y. So the input's x, and then the output of the labels is y. So for every input-output pair that you have in your examples, so input being x, the output being y, compute the squared difference between what the output's supposed to be and what my function says it is. Okay, so I'm going to test out my choice of function on the examples that I have. Okay? And so for each of them, I'm going to sum up this difference. So actually, this is called the squared loss. And so I need to pass along, the x, the y, and then the function that I evaluate on all the x's. And so here, I'm just going to take the squared. I'll take the difference first. So it's going to be the difference between the label that I have and the function evaluated on the inputs, actually squared, and then I'm going to sum that up. So I might as well actually just return it straight up. So I'll just sum those. So this is actually an array here. This is an array of all the labels, and then this is evaluating the array of all the inputs, taking the difference between the two, which is also an array, squaring that array, and then summing all the elements up in it. That is what this is saying as an equation. And so what I'll do here is I'll make a different kind of plot where I will try a bunch of different c's. So let me do the following. I will make an array of all the c's that I'm going to try. Maybe I'll try the c's between let's see, maybe between -3 and 3, maybe I'll take 100 possible c's. So I'm going to try out 100 different functions, and let me apply the objective function to each one on the labeled examples that I have. So actually, I guess, yeah, okay, so the inputs here is called x, and the outputs is called labels. So what I'll do is I'll just loop through all the possible c's. I'll define my function as, it takes an input, and I will choose, so my particular c, and I'll plug that in. So, okay, so I'm supposed to be calling this loss function here. Whoops. Oh, crap. What did I just do? Okay. So fc, and then, so I'm going to plug in the c, and then I'll pass along the x. That is my loss function. So I'm just, I'm using those anonymous functions like we used back in homework 2 with the FM synthesis to, pull out a particular choice of function, so the one where c is equal to c, and then I'll pass that function along to the squared loss. And let me actually make an array of the losses, which is parallel to c's. And so I'll say, okay, the losses at index I is equal to the loss squared function. Applying the inputs x, and then the labels, and then this particular choice of function. And I did that twice in a row now. Okay, so now let's plot the result. And so what I would like to do is actually plot the losses versus the choice of c on the x-axis. And look at that next to the data. Okay, so here's what we see. We see that the loss function here, so that's what this is. So I'll say, the data points is what we plotted first, but now I'm plotting the loss function. Actually, maybe let me go a little bit finer resolution than this. Let me go down to, I'll take 1,000 samples here. Okay. And so what I see is, okay, the loss function is not as good over here. It wouldn't be as smart to pick the threshold here to say, okay, everything greater than -3 is a 1. We'd be getting a lot of stuff wrong, right? And so we see a pretty big discrepancy here. But around c equals 0.8-ish, we see that we're minimizing this function. And so we, some choice in this range here is going to be the best choice that we can make on this data of all of the functions that we restricted ourselves to, right? So if we're restricting ourselves to this function here, it looks like the best c that you can choose is around 0.75, 0.8-ish. Okay, so I'm just going to have you do a quick exercise that makes that explicit, that explicitly returns the c that minimizes in this particular example. But then we'll continue on to show you where this maybe is not the best way to do it in general.